So we worked through the example where we had direct variation that meant y varies directly as x, and we had y equals kx. We also have the case where we have direct variation of what we call of an nth power, where n here is just a placeholder for some number that we would have. So if we see a statement similarly to y varies directly to some power of x, like squaring of x, or the cube of x, the square root, something like that, that indicates an exponent happening on that x, then we're going to have y equal to k times x to whatever that power would be. Here we're calling that the letter n, where we still have that k is our variation constant, or also called constant of proportionality. So an example of this, we have that the distance d of an object falls on Earth is directly proportional to the square of the time. So that's going to be t squared. And then we also have that after 6 seconds, an object has fallen 576 feet. So now we want to be able to give the model for this that will tell us the distance d of an object after t seconds. So let's start off with our equation that we have from the sentence up above. We have that our distance d is directly proportional, so that means equal to k times, and then after that we have that's directly proportional to the square of the time, so that's going to be our time squared. So this gives us the starting model, d equal to k times t squared. And now we need to use the data that we have, that after 6 seconds, the object has fallen 576 feet. So we can replace our time and distance with those two. So we have that 576 feet is equal to k times 6 squared. So that gives us 576 is equal to k times 36. So now to get k by itself, we just have to divide both sides by 36. So that then gives us that k is equal to 16. So now our one last step to finish this part off and give us an equation that we can use for the next one is to go back to that model that we wrote at the beginning, d equal to k times t squared, and just replace k with 16. So we have that the distance is equal to 16 times t squared. And now for the next part, we are asked, how far will it fall in 8 seconds? So that means we need to let t equal to 8 and then evaluate our equation. So that means our distance is going to be equal to 16 times 8 squared. And then that should then give you 1,024. And now we need our unit. This is our distance. We need to go back to the unit we used for distance when evaluating k, which up above, we had that as being feet. So this is 1,024 feet. we have one more example here to work through with this. And this one, we are told that the distance to the horizon is directly proportional to the square root of the elevation of the observer. And a person 36 feet above the water can see for 7.44 miles. And the first thing that I want to do here is to just write the equation with only the variables. This step is what a lot of the problems on your WebAssign homework are going to ask you to work through first, to just put in what the variable or the equation would look like with the variables and anything happening to any of the variables. So here we have that our distance, which I'm going to call d, is directly proportional to the square root of the elevation. So that means d is equal to k, and then I want to take the square root of the elevation. So square root, and here I'm letting elevation be h for their height. So I have the square root of h. And now for the next part, I want to use my given data to find out what k is. Well, we have that when their height is equal to 36, then their distance that they can see is equal to 7.44 miles. So we can put those into our equation from part A to evaluate k. So this means 7.44 is equal to k times the square root of 36. So now to solve for k is being multiplied by the square root of 36. So we just have to divide both sides by the square root of 36. So now that gives us that k is equal to 7.44 divided by the square root of 36, and you should get 1.24 for k. So now let's write the model. We're going to look at our equation from part A, and we're going to ignore the data that we had. We only use that to find k, and we're going to replace k now with 1.24. So d is equal to 1.24 times the square root of h. And now we have a couple quick questions that we can answer regarding this situation. We are asked, how far can a person see if they are 64 feet above the water? So this is telling us their height. So this means we want to replace h with 64. And then we need to solve. So their distance that they can see is equal to 1.24 times the square root of 64. And that should then give you 9.92 when you put that into a calculator. And we need our unit for this. Our distance d for our model was told it was given in miles. So this is 9.92 miles. The next question that we are asked, if a person can see 8.68 miles, what is their height above the water? So now in our model, we need to replace distance with 8.68. And then we have to take that to solve for their height, h. So 8.68 is equal to 1.24 times the square root of h. And this one's a bit more work because I want to solve for h, but there's multiple things happening to it. So we need to work in the opposite order of our order of operations to get h by itself. So order of operations would tell us we would do the square root first, but I want to do that last because that's the first thing that would be happening to h. So instead, I need to deal with the 1.24 because that has multiplication, which comes after our square roots. So let's divide both sides by 1.24. So this then gives us that 8.68 divided by 1.24, that is 7, and that's equal to our square root of h. And now I can undo the square root. How we undo a square root is simply just squaring it. The square root and the squares undo each other, but if I square one side of my equation, I also need to square the other side. So this gives us that 49 is equal to h. So their height is going to be 49 feet above the water.